Welcome everybody to Basel, Tuesday afternoon. I know it's a little bit low energy level, and Scott made already a very, very cool presentation about all the market numbers, so there's not too much to add on that one. And no worry, I will not try to sell you something today. So we had probably some pitches on that one, so I will stop that. I work for Effect Photonics. Some people might not know it. I just got the question, are you the company who bought the DSP team from Viasat? And yes, the answer is yes, and I will talk about that a little bit, what we see on that side a little bit later. I give you just 2 slides on Effect Photonics because not everybody knows it, but you also understand the context on the market update, how we see it, obviously will it bias from our corner, how we look at the market, and on the technology trends to address some of the problems. So it's a light discussion, some food for thought only, details, it's more for a Tuesday afternoon to digest a little bit. So what are we doing? We looked at the industry. You saw the discussion about the Coherent on the 400G, SETR Plus, 100G discussion, some announcements not too long ago on Coherent going closer to the access from some of the market players here, and of course the discussion about the 800G on the other extreme on that side. So the markets we are going to is mainly the 5G, so we have some stuff on that one. We do access, as we are a semicon company, so really high volume. So bear with me, I will not talk about too much about the high performance long haul, ultra long haul market, more about the problems and topics to discuss when it comes more to access, high volume, and really how to get to high volume in terms of cost, power consumption, and a stable supply chain. I think we all experienced the last 2 years a little bit a bump in that one, and it's still not fixed yet. So you have to do a little bit more than just the status quo. And then obviously also the cloud, and just got mentioned, Cloud Edge will also change a little bit. The Cloud Edge has a slightly different requirements in terms of data rates, and of course in terms of power consumption, it's a little more stringent than within the main centers. What we provide is, of course, on the underlying technologies, we can provide you the pluggables, but basically our technology core underlying that is what we would call the sub-assemblies and the ASICs. And what do we mean with that? Yeah, ASICs is a DSP, so as we just got the question, so we own our own DSP design. It's maybe not so publicly known for everybody, but if you want to have more known, you can come to us. So some people know we made a public acquisition from the Viasat design team, who was one of the first ones, I think the first Acacia DSP team, they were involved in that design. I think it's publicly known. There had been so far more a design service company, and now within Effect Photonics, we also can tape out the DSPs. The other part, because different than most in the booth here, we have our own 3.5 competence. So we have our own PDKs. It's one of the few ones. That means we own the laser source. We do indium phosphide. So we have our own laser, our own ITLAs in case you need it. But also we can do a step further. So we have some patents like on an integrated wavelength locker. So we don't need to put something on top of it in terms of size. We can integrate it. So we can integrate all active optical components on the chip. You can have a Mach-Sender modulator, a wavelength locker, an optical amplifier, a SOAR, something like that, whatever we need. It doesn't mean we integrate everything every time. We make a very diligent choice depending on the product and the application where the product should go for. We are not so much known. We work more in the background with a lot of players who might want to have custom sources or something like that. So, and last but not least, it's nice to have this as technology. Every research institute can have technology, but the challenge was more to develop a design process which works with the existing ecosystem. So we are fabless, like differently like some of the other players here. We work with the large fabs in Europe as well as in Asia, where we can source. So we are able to have our PDKs working with the existing process of these fabs. And the same is for the product design itself. We made an announcement, for example, for co-development on Coherent with Photonics, so we can run on the big contract manufacturers. So it's really We are more looking for the access market, the high volume market, where semicon makes sense. If you have high performance, low volume, high margin, you have different choices in the design, but we see like the trend for high volume, you need to go to semicon, high integration as much as it makes sense at a certain given time, but also the ability to have a stable supply chain via contract manufacturers. And the challenge is not, you go there, but you have to make a design which works with their existing processes. So that's a little bit about effect photonics. So when we talk about edge computers, data center infrastructure, and where this is going, at least one market number Scott didn't show yet, that is just for the cloud edge. And everybody likes growth, so do we. So it's one of the new fields where you have high growth rates in a very kind of an exponential dimension. So obviously you could have started with a technology to serve, let's say, up to now, but you will see in the next years with the high growth rates, you have to probably switch over in more high volume production technologies. And of course, it can be anywhere. It can be closer to the enterprise, can be closer to residential areas if you want to have a cloud edge center there, or closer to certain hotspots on the mobile device. So there's not really a dependency on the end access requirement. It just drops out further and further. And then the question is, of course, what are the data speeds there? And as we know, different than the core where performance is kind of a little bit a driving factor, access is all about power consumption and cost. The stuff nobody likes to work in. It's a little boring and tedious. So you have different types of people who enjoy focusing, optimizing towards power consumption. So when we see the history of the access network, there was a lot of direct detect, and there's still a lot of demand for direct detect, like 10G, and we saw some announcement on SFP 28 for the mobile backhaul network. Let it be a classical direct detect but short distance, or some announcement on a PAM4 which matches the dispersion compensation limitations. So that's all fine. The alternative, always the question was, can you make a coherent? And technically yes, and the but is, the moment I have a coherent module, I need a DSP. And the DSP means I have high power consumption, which is really not something you want to have in the access. The next one is, of course, you have high cost. We all know DSPs are not too many suppliers out there. It adds a significant burden on the cost side. So also not very nice. And last but not least, a coherent module still today, if you look at the build-up, at least in the classical way, gold boxing to some extent, it's very complex to manufacture. So there is a ceiling like what can be done, and that you see this in the output. So some market numbers are driven not so much by the market, but more by what can the supply be at this time. So there's a constrained situation. And we are not smarter than anybody else. It's just we looked at it like, damn it, not sure how to fix it. And we see, of course, like some announcement on a 100G ZR DSP coming out, so with low power for QSP28. So people are looking into it. We are not the only ones in the industry, because we have to fix a problem in the access or in the cloud edge. Because what do you do if I need a 40 or 80 kilometer link on 10G? I need more capacity. If the price point is not right, like I try to push it out as long as I can, but at some stage there needs to be a solution. So we have an industry problem on that side. It's a very clear defined how to get to higher speed rates on these links. So what are some technological approaches we see like in this area? The first step is what we saw, for example, also from, I think Intel made an announcement, thinking about laser arrays. We saw on the high end, like, okay, 800G, 160, but is it 1 times 160? Is it 2 times 800G? Is it 4 times 400G? When you start integrating on a chip, you can optimize multi-laser arrays power consumption. So it's a question like, do you push for high baud rates or do you go for multi-laser arrays? Now, if you have to buy the laser, it's a knockoff situation kind of, because it's very expensive. We can, of course, make you a nice laser because we can integrate it on a very small chip. The next thing is the question about full integration. Today still we have a lot of discrete buildups in the Coherent side. That's why you have the gold boxing. It's a piece of art. Every engineer loves it. If you see the pictures, it's really cool, but it's also very expensive. So the finance department doesn't like it. The engineers do. So full integration would be one option to address it. Another topic, and that's maybe a new one, probably the first time we talk about it. Today, if you buy a DSP, usually to sell it to somebody who has an internal vertical integration, they have their own silicon photonic program, and then they buy somewhere a laser and put modules together. So all the DSPs are optimized for silicon photonics. So each material, as in physics, has pros and cons, some strengths, some weaknesses. So the DSP usually tries to take care about the weaknesses of silicon photonics to have an optimized module solution. If you go for integration indium phosphide, you have different problems. You have different strengths. Yeah? You have a much higher output power on the transmit side. The receive side is a little bit not so nice compared to it. But what has not been done so far, and which provides a huge opportunity for improvements in the future, is optimizing the DSPs for indium phosphide. And then we need to see where we get out there. And that is an untapped research area, opportunity area to go even further into performance and power consumption optimization. Last but not least is always a design for the ecosystem. There's so many people here doing great jobs, have a lot of innovation. I mean, it's quite amazing what every booth has to do, and also go to the smaller booths. There's a lot of smart people who think about details in some areas. So you don't have to invent everything yourself. The question is, how can I start building a culture for design for the existing ecosystem to drive down the cost and up the volume? So what are some of the options? So if you look at that one just at a high level, and you might have your own internal metrics on that, but if you go very simple and we say, okay, we want to go to 1.6T, yeah, you can have a high baud rate 1.6T, that's clear. I can have 4 times a 400G module, external solution, then I have, it's of course easy, I can buy that, the complexity is medium, faceplate density is low, but I need an external mux. It's installation-wise, power loss, not perfect, but you can go ahead and deploy it immediately. Then you have a high baud rate, the other extreme. Obviously, the complexity extremely high. Yeah, I mean, it's a lot of money spent into it, and if you want to make a DSP on that one, that will be very expensive and a lot of upfront investment. Faceplate density is also high, but you don't need external muxes. That's the cool thing. You want to get rid of it, perfect. Or another extreme, and there are different flavors in between, we can also talk about 2 times 800, is, for example, one module, but 4 times 400G. What does it mean? I have one module. The complexity is also relatively low. 400G is understood. The faceplate density is also high, obviously, and I need to have 4 laser sources, and I don't need an external mux. That's kind of one of the things, and I don't have the final answer. If you ask me where is it going, I don't know. So we are talking about it. There's always pros and cons of certain cost items, power consumption, and what you're looking for. But we will see a trend that the straightforward 1 time 100, 1 time 400, 1 time 800 or 1.6T or 3.2 will probably break apart, and we will see more solutions going to a 2 times 800, 4 times 400, 4 times 800 maybe for a 3.2 tera, for example. It's much easier from the timelines when you want to deploy, or when the hyperscalers have the deploy cycles to hit with the technology the market. So the laser part will become more important, like how to integrate it very small in your system. The next thing is, and I lent me something from the Apple, because everybody I hope knows it, is integration. High integration always won, at least in the electronics industry. We're on the photonics side, but you can learn a lot from them. On the electronics side, we saw that high integration always won the cost curve. And even a good example, because it's public, if you look about the development, like when we had a more discrete build-up from Apple, each generation moved up, you had a bit more power consumption, then they optimized a bit on the power consumption, but the performance didn't increase so much. The big change came when they came with the M1. So instead of having all the functions, the GPU, the RAM, and the CPU separate but integrated in a single chip, you take out a lot of intra-connection losses. That means they increase the performance, at the same time dramatically reduce the power consumption. And that's kind of the point which is important in the access. Not so much in the core, I give you that, that's performance and there are different options. But when it comes to access high volume, high integration is usually the key. So if I can integrate and get away from the discrete builds into single chip designs, power consumption will go down dramatically. And we did some samples in-house with different degrees of integration, and we have very nice data, and you can, if you want to have a talk, we can talk about it, but you can see how the power consumption goes down because of removing the losses in between. You have, of course, some other drawbacks, like you have to look at the yield, so there's always a drawback. How much do you go for power consumption versus yield, because yield is cost, and in the access you don't like power, but you also don't like cost. So there are some compromises to be made, but that's kind of a huge trend, and that's a good example from the electronics world. And if you don't know where to go, look at them, or look at the radio guys when you think about photonics. They went through a lot of the problems we have these days and went for certain solutions. The other part is, and that's very new, when we have the different DSP with the SiP, and we have the power consumption requirement drive power. We see on the right side what we have is a standard DSP and the silicon photonic PIC. That's kind of the state of today. If you go down and use an indium phosphide and have a standard DSP as it's designed yet with indium phosphide, you see already a little bit the power consumption slightly lower, but not too much, but the requirement for the drive power is already much lower. What has not been yet really taken advantage of when you own the DSP and understand indium phosphide, if you integrate both of them, that you make a different mode. Yeah? DSPs have multiple modes. You can add another mode which is optimizing the DSP to drive down the power consumptions. And there's a long list of things, but a few ones I want to give you for food for thought. We're here to learn something, so just take it with you and then you can tell at home. One thing is to substantially low drive voltage required for the indium phosphide modulator. That allows you to have the possibility to eliminate some of the components, such like the RF drivers. I don't need that if I use indium phosphide. So I get rid of it, power consumption goes down. Another one is if I think about driving the modulator directly from the DSP that I have enough power over there, without any intermediate electronics, which would also reduce the power consumption. That's not possible with a standard one. And another one is if you think about signal conditioning to minimize some of the nonlinearities in the modulator to improve the performance. So there's a long list of things you can do if you think about indium phosphide integrating with DSPs to give you an advantage of the status quo of the industry with laser, silicon photonics, DSP, some optical coupling, and these kinds of things where you have internal losses which drive you down to the minus 10 dBm. Yeah? Just an example, typically indium phosphide just plugs power into the fiber at least 0 to plus something, because you don't have any optical losses within it, which means I don't need an internal amplifier which drives the noise up as well, which then needs a noise filter at the end. All these building blocks are gone. So, but here it's really talking about the DSP has a lot of room when you optimize it for indium phosphide, which so far hasn't been done in the industry. So we have a big chance that there are better solutions coming in the future if you think about a little bit out of the box from the status quo. Last but not least, yeah, that doesn't help if I only can build a few thousand a year. We are fed up with the supply chain issues. Everybody's asking for modules and deployments, and everybody's waiting. So you have the challenge to design it that you can work it with any like contract manufacturer and any large wafer supplier. So that means like I go like state-of-the-art performance, but packaged like electronics. So we have flip chip technology, what we discussed also today. We have high volume packaging, and here you see on the bottom like a very fully automatic standard production line to get all these modules out of the chip. The nice thing is if you integrate a lot of function on a single die, you can also test already on the die. So I don't only get a no-go die and then I package it and then I test it and then it fails and I throw it away. I can do all the optical components which are on the die, or I can do testing on the die, and I can filter out all the non-workable ones. So I don't even go into the process of packaging them and assembling in and something like that and then filter it out. So the fault isolation starts at the beginning of the production line, not at the end. And that drives, of course, down the cost, which we all like, because we want to have cheap, coherent stuff for the access and for the cloud edge. That's it from my side for today. Just giving you some food for thought for a Tuesday afternoon. It's very promising. There's still a lot of things we can do as an industry to get coherent closer to the access or the cloud edge, to lower cost points. And yeah, it will be interesting times we're in. Thank you.
Thank you. So are there any questions?
No.
Okay, so actually I would, okay.
I was going to ask you, so is two companies, I think, do indium phosphide integration, but in silicon photonics is the PDKs from several CMOS fabs. How do you compare the two of them at this point in time? Are you still very custom in indium phosphide?
Yeah, you're absolutely pointing the right thing. So if you go to a silicon photonic, of course, the PDKs are available, so that's why it makes it attractive. Everybody can use a PDK, which has the advantage you can do something yourself. It has a disadvantage, also everybody else can do it. So where's my differentiator? Indium phosphide is still certainly a very complex technology, and therefore is kind of more proprietary in that sense. You cannot just go somewhere. So in our case, we are lucky we own the PDKs, but of course we also work with some of the fabs that they start maybe potentially licensing in the next year, some of the PDKs. But I mean, the nice thing is, I mean, today you have very few laser suppliers. You can also come to us as a laser supplier, but we can also do a little bit more than just a laser if you need that. Yeah? But definitely, that is one way to go. I just encourage everybody, there is more than just one material. Think about it, think out of the box. I don't know if indium phosphide is the final answer to everything. In 5 years, somebody comes with something else around the corner. So keep it open and think about it. But the good thing is, from an ecosystem 3.5, I mean, we have the big fabs in Taiwan or whatever. It's an established process. You just have to understand it. And you have some work to make your design according to the existing process. Fair enough. But once you have it, you have a high volume, very nice material to work with.
Another one, a quick one from my side. So yesterday we talked about new fiber types, multi-core, also for metro applications in busy areas, which are going to be difficult, but I understood that that might be also needed than a new transceiver design. Is this something you're looking at as well?
So obviously we are working with the typical fiber suppliers, and we talk hollow core, multi-core, these kinds of things. We look into it. There are pros and cons to the fiber types. Also, you have to first lay it, which is very cost sensitive, and especially in the access, you want to use your already existing infrastructure as long as you can. So changing to a different fiber type basically breaks this logic apart. But yes, we have a very, very good research department run, and they make tests on a lot of hollow core or other fiber types as well. Hollow core in particular, for example, for the data center, if you have a hot today, the latency end-to-end means a 60-kilometer range. But if I can get maybe with hollow core up to 80 kilometers, a third more latency, the real estate price goes down immediately. So it's very attractive, especially. And with the deployments of Cloud Edge and other ones where you have hot deployments, these things are interesting, but at the same time, the fiber supplier says, yeah, but you have some other problems because there's something in the fiber, that's a different fiber in the splicing, and something happens. So it's not really ready for commercial deployment, but yeah, we work with them.
All right then. Thank you very much again.
Thanks.